okay, let's try it this way. Sorry. Well, okay, of course. Yeah. So this is okay. What I'm going to talk about is based on that paper here, also on JHEP, and it's work done with Emilian Dudas, who was already mentioned as my PhD advisor, and Gabriele Casagrande, who's currently a student of Emilian. So yeah, and yeah, the topic will be positivity bounds on nonlinear supersymmetry and what they imply and suggest about this very framework of nonlinear supersymmetry that I'll try to review. But first, let me give you a couple of motivations for that work. We started thinking about this idea of positivity bounds in relationship with nonlinear supersymmetry because of some features that were seen in the way gravitinos behave in supergravity cosmology, so in cosmology described within the framework of supergravity. And in particular, it was observed in the recent years in the literature that there were some issues with gravitino propagation in models of inflation described within supergravity. In particular, in that paper here, in 2021, these authors noticed that at the end of inflation, when the inflate and scalar field like oscillates around its potential and slowly rehits the universe, that in some models, the gravitino sound speed, so the speed that dictates the propagation of gravitinos in the universe at that time, was periodically vanishing. And at the point where it periodically vanishes, as the inflaton oscillates, there could be a massive production of gravitinos that would be an issue for today cosmology. So okay, that was noticed in some specific inflation model and some specific description of the gravitino in those papers. And then this paper came and realized that this feature could be avoided in some other models, but at the same time, by doing so, they noticed that there could be an even more severe issue associated with propagation of gravitinos, which would be the loss of causality. In particular, the fact that gravitinos in some models seem to propagate faster than light, that the equations of motion would be compatible with a propagation faster than light, leading to a lot of the known causality issues. So what we started thinking about this afterwards, and we realized that this issue related to causality was associated with the use in those models of something called nonlinear supersymmetry, and in particular things called constrained superfields. So I'll review all of that in the next slides, but that's those were the ingredients that we pinned down as probably the source of these issues that were identified in this series of paper. And we started asking, well, are there consistency requirements that we should impose on top of this when we use this kind of notions so that the whole approach and the whole model is consistent. So yeah, that was the background of what got us thinking about positivity bounds in nonlinear supersymmetry. So yeah, of course, sorry, I should say, feel free to interrupt. So I don't see the faces of people now, but just shout if you have a question or a remark, and I'm happy to discuss.
Thank you so much.
Yeah.
We will do that.
Cool, thanks. Great. Yeah, so, okay, those were motivations. Now let me tell you a bit more about nonlinear supersymmetry, or what it represents and what it represents technically, and in particular, some realization of nonlinear supersymmetry that bears the name constrained superfields. So first of all, okay, before I tell you what nonlinear supersymmetry is, to tell you what nonlinear supersymmetry is, I should then answer the question, when do we use it? When do we need nonlinear supersymmetry? And we need it when we want to describe the low energy or the effective field theory description of a theory that undergoes spontaneously broken supersymmetry. So when we're dealing with energies much below the scale at which the spontaneous symmetry breaking of supersymmetry occurs, then we could use an effective description at that scale, and nonlinear supersymmetry is simply the name we give to the way supersymmetry manifests itself in those low energy descriptions. So it's something that is useful, for instance, in cosmology. In cosmology, you have broken time translation, you have positive vacuum energies, all of these things that break the supersymmetry of the model that you make live on such a background, right? So, for instance, the dynamics of inflation in cosmology, for instance, are expected to spontaneously break supersymmetry and may require such a formalism. It's also useful in string theory. So, for instance, there are these extended objects that kind of look like defects in string theory called branes. And to describe those branes, you have like actions, like field theories that live on those branes, and the presence of the branes break part of the supersymmetries of the underlying string theory. And when you write the brane actions, so the action that describes the dynamics of the brain, some of the modes are going to be, well, the behavior of the mode are going to be dictated by the fact that supersymmetry is spontaneously broken. More generally, it's useful, for instance, with when we think a bit more about phenomenology, if the lightest supersymmetric particle, the LSP, is the gravitino. So for instance, if you imagine that supersymmetry breaking is mediated through gauge interactions, you have the following, you expect the following rough formula for the mass of the gravitino, which suggests that the mass of the gravitino is much lighter than, for instance, the superpartners of the standard model particles. So in those cases, you may find yourself in some energy regimes where you're left with a gravitino and let's say the standard model degrees of freedom. So that's a case where you're much below the scale where any kind of supersymmetry is apparent, but you still have a gravitino that suggests that you should link it to some spontaneously broken hidden supersymmetry. And yeah, it turns out that when you try to think about what could be the generic prediction of spontaneous breaking of supersymmetry and how it could manifest itself below the scale of breaking, and it turns out that the only thing that you have for sure in the deep IR, in theories that spontaneously break supersymmetries, would be either a massless Goldstino, so a massless Goldstone fermion if you deal with rigid supersymmetry, so supersymmetry that is a global symmetry of space-time, or if you think about supergravity, the local version of supersymmetry, then the prediction is that you have this massive gauge field, fermion gauge field of supersymmetry that is the gravitino. But that's pretty much it. You don't have any kind of other selection rules that would be universal. So that suggests that if you want to describe the dynamics of a Goldstino of a gravitino, you should be able to couple it to roughly any kind of matter that could be the remnants of a fully supersymmetric theory. So yeah, so basically nonlinear supersymmetry is the framework through which you can couple such a particle, a Goldstino or gravitino, to any kind of matter in a way that remembers that hidden at high energies there is an active supersymmetry. So let's see how that is done.
Sorry, in the case in which in the scenario where the gravitino is of very low mass, one can use the Goldstino.
That's right.
The amplitudes expressed in terms of the Goldstino, a
That's
sort
right.
of equivalence theorem like in the usual gauge theories, no?
Absolutely, absolutely. Yeah, I'll mention that a bit later, but indeed, yeah, that's absolutely right. Yeah, if you were to scatter, let's say, the longitudinal component of the gravitino against anything, right? If this scattering happens at energies much higher than the gravitino mass, indeed, this kind of scattering is very much is perfectly captured by the Goldstino scattering that would be equivalent in the theory of rigid supersymmetry. Yeah, that's absolutely right. Yeah, actually, I'll use that fact a bit later to simplify
but
my life.
The simple fact that the mass of gravitino is very low, it means that the transverse component of the gravitino are essentially decoupled, and what is actually working is the longitudinal part of Goldstino.
Right. Yeah, absolutely. Yeah. I agree with that. Yeah.
Okay, thanks. Go ahead.
Yeah. Okay. So yeah, this is roughly the picture of when you might want to use nonlinear supersymmetry, and that still hasn't answered the question how do you build it, but how does it look in practice? And I'll be discussing two options, one for historical reason, and the other one because that's actually what I'm going to do. So when you think about spontaneously broken symmetries and how you should parameterize the induced dynamics at low energies, there's like this very general formalism that applies for any of them that I'll be calling option one. That is the formalism of Callan, Coleman, West, Zumino, CCWZ, that is basically telling you that there is a universal way of describing the low energy dynamics of Goldstone bosons. And the idea behind this is to, if you have a group, a symmetric group that is broken from the full group G to a subgroup H, you can interpret the Goldstone bosons as coordinates on the coset space. So this space I mean, it's a manifold that has coordinates, and you can like have you can choose a one-to-one mapping between those coordinates on the space and the Goldstone bosons. That gives you some kind of a natural parameterization of what the Goldstone bosons should be. And that also gives you a natural way of coupling those objects to any kind of matter. And the nice thing is that you can couple it to any kind of matter as soon as you know the transformation of that matter under H only, and not the full G. So it allows you to, if you specify that breaking pattern, you get immediately Goldstone bosons. And you just have to specify what are the things that survive until low energies, and how do they behave under the symmetries that remain at low energies. So for instance, in the case of the breaking of a symmetry ON to ON minus 1, which is the canonical example of the nonlinear sigma model, the Goldstone bosons, like this coset space, can be parameterized by an object of that form. So you have these generators here, which are associated with the directions of the coset space, and the directions, like the coordinates, would be the Goldstone bosons. So this would be all the matrices that act non-trivially, that don't leave this vector here invariant, for instance. And then, okay, I'm not telling you how to do it, but there are like very precise rules in this paper on that tell you how you can couple these guys, the Goldstone bosons, to fields as soon as you know the transformation just under H of those fields. So for instance, you just have to know which representation those guys have under ON-1 to couple them to the Goldstone in a way that like is compatible with the full but broken ON symmetry. And the idea behind this is that there's a way of systematically, in any kind of model, there's a way of like dressing the UV field in a way so that you completely cancel the full G transformation and kind of project it under along H. So you have an expression of that sort where you can like project along the Goldstone, thanks to the Goldstone boson, this UV field, which is a full representation of the full group G, onto an object that happens to be just a faithful representation of H. Okay, but that's something you would do. That's the way the Goldstone boson can somewhat like discharge the G charge of this object. But okay, that's like the picture you have when you map from the UV to the IR. It doesn't really matter you don't have to know this kind of mapping. You just have to know that those kind of objects exist. You just specify how they behave, and you can build a full theory. So usually this picture is thought of in the case of the spontaneous breaking of internal symmetries, but the same happens for space-time symmetries, and in particular for supersymmetry. So you can apply, at least you can get an inspiration from this idea and these techniques for in the case of supersymmetry, where you break your super Poincaré group down to just a Poincaré group that you observe at low energies. And this was first done by Volkov and Akulov in this seminal paper, which actually happens to be I think the first 4D field theory that has supersymmetry. Named, for instance, the West-Zumino model that everyone knows came just 1 year later. So that's a very important
just a
paper.
minute. The rules of CCWZ can be applied also to superfields?
Yes, they can. Sorry, I'm used.
I mean, the construction of the invariants, as it is done in that paper,
right,
is directly applicable to superfield, or one must go to components?
Let's see. Yeah, I'm better. I'm more used to the component picture, but let's see. Is there? Yeah, I think there should be a way of. Let's see. So what you can. I have a doubt. Sorry.
Okay.
Let's see. How does it work? No, I think you can do it. Yeah, I think there's a way of doing it at the level of superfields. Maybe you can. No, I think, sorry, I'm slowly building towards it, but yeah, I think there are ways of changing the. Yeah, right, good. There are ways of defining something that is called the Goldstone superfield from. So yeah, okay, good. So okay, the way I know how to do it is in 2 steps. So maybe it's a bit cheating, but what you can do is to like do it at the level of components to define the Goldstino, then use that Goldstino to build a superfield, and then use that superfield to to build those matter representations that have the simpler transformations. At least I've always seen the construction this way. So you first formulate it at the level of just fields, not superfields, and you can like uplift that construction to full superfields. But I don't know if the result can be reached immediately as one step. Yeah, sorry,
Okay.
that's not answering the question really. But so there is a story that you can say at the level of superfields, but it's always I've always seen it indirectly, like first at the level of fields and then the level of superfields. So yeah, that's a good point. I'm not sure actually. It's probably known, but I don't know. Yeah. So yeah, good. So I was saying that this, at least the philosophy behind this, can be applied to supersymmetry, where you just interpret this as the super Poincare group, and this as the Poincare group, and these things are as the broken generators that are the generators of the supersymmetry. And yeah, instead of the Goldstone bosons, the would-be coordinate along those fermionic generators that describe the broken supersymmetries is what we define as the Goldstino. So it's the Goldstone fermion of broken supersymmetry. And in the case of local supersymmetry, it would play the role of the longitudinal component of the gravity. And yeah, so the result that Volkov and Akulov reached, which is basically the supersymmetry version of that story, is the following. The result is the following. So they found that transformation. So this is the fermionic field, and this would be the supersymmetry transformation of that fermionic field. So you see, it's kind of a weird object with respect to what you might.
Quentin, I think that the slides are not appearing as in your because just now it appears the formulas. Okay.
Okay, sorry about that. Well, so you can see the pink box now.
Yes.
Okay, very good. Okay, well, no, probably some. Yeah, sorry for the delay. Yeah, so the transformation you're getting when you're playing that game is the following. So the first thing here is the supersymmetry transformation of the Goldstino. So it's some sort of a weird transformation because there's no boson in it. So it doesn't map a fermion to a boson. It's just a transformation of a fermion as a function of itself, which is something that we should not be shocked by. So when you think about the U1 transformation of a Goldstone boson, for instance, it's just a shift, and it's the Goldstone boson is a real quantity. It's not mixed with another real quantity into a complex object on which U1 would act. So the same happens here. As now that the symmetry is broken, it doesn't have to relate the fermion and the boson, and this is a perfectly valid supersymmetry transformation that respects the supersymmetry algebra and so on. So that's the result you get if you play that game, and that's the result of Volkov-Akulov. And you can also write the interacting theory of those objects, which would be the equivalent of the interacting theory of pions in the case of internal symmetry breaking. And yeah, there's a very quick way of writing the Lagrangian using this determinant of this 4x4 matrix here. Yeah, okay, that's the result.
Here F is the scale of
that's right.
The breaking of the symmetry.
Yeah, that's right. This F here is something that has dimension 2, like mass dimension 2, and yeah, that should be thought of as roughly the square of the scale at which supersymmetry is broken. Yeah.
So epsilon is a dimension of -1/2.
That's right. Yeah, this is I'm using this. Yeah, I'm using this convention indeed. Yeah. This thing has dimension -1/2, so that it maps dimension 1 scalar. Right? So that the transformation of the dimension 1 scalar involves a dimension 3 half fermion, and this -1/2 is there to cancel this thing. Yeah, that's right.
And I mean, these are the Weil spinors.
That's right. Yeah. Those are written in terms of Weil spinors. That's right. Yeah. I'm using those. Yeah. Good. Thanks. Yeah. Those are. Yeah. I'll be. Yeah. Everywhere here, I'll be using this 2x2. Well, this two component spinor notation. So I'll have these sigma matrices instead of the gamma mu. The gamma mu matrices. So yeah, all of these things are Weil fermions. Yeah.
And by the CCWZ, I will be able to construct the more general invariants.
Yeah. You can
under the nonlinear supersymmetry.
That's right. Yeah. So this slide here only shows like the self interaction of the Goldstone with itself, but you can carry this procedure. so that you also include matter fields, and that would be what I show here. So I'm not writing the Lagrangian, that is slightly more involved, but you can in the same way as you can use the H transformation of matter to couple it to Goldstone bosons and like uplift the H transformation to a full G invariance. For supersymmetry, for broken supersymmetry, you can uplift the Poincaré transformations of the fields into a transformation that allows the Lagrangian to be fully supersymmetric. So in particular, supersymmetry would act here on matter fields in this way. So what you see, you can realize that it really looks like a space-time transformation. So this is just the space-time. So this would be a field, so any field, not necessarily Fermion. Sorry, probably the notation is a bit confusing, but that's any kind of matter field. That would be the transformation. That would be the supersymmetry transformation of this field that really acts like a translation, like a local Poincaré transformation. So you just have to build the supersymmetric invariance. You just need to know these Poincaré representations. And then this law tells you how you can uplift those representations of Poincaré to something that has the right invariance to build a fully supersymmetric Lagrangians. Yeah. So this would be also the result. This would be the equivalent of what CCWs find as the G transformation of fields as soon as you know their H transformation. So here H is Poincaré and G would be the full super Poincaré. And yeah, if you interpret these formulas for supersymmetry, the one that appear here, they would suggest that matter field should transform like this. And yeah, that's how their behavior under translations, which are unbroken, uplift to the full supersymmetry.
Okay.
Yeah. So I'm not very explicit at that stage because that's not the formalism I'm going to rely on, but I think it's important historically to understand that it exists. That's also how this business started. But so this is a very generic formalism. As soon as you have Brocken supersymmetry, you can like relabel your field, redefine your field so that it matches that picture. So whatever the Goldstino you start from, wherever it comes from, you can always redefine it, mix it with fields, etc., so that it behaves exactly like that. And similarly for the matter fields, you can always go back to this formulation, but it's not always the most appropriate or the simplest. I wanted to say that this formalism allows you, as I was anticipating a bit earlier, that any kind of matter can be coupled to a Goldstino without, for instance, the need of auxiliary field or without the need of a full supersymmetry multiplet. The formalism is compatible with this. But yeah, as I was saying, it's not always the simplest to deal with or the most appropriate to the physical picture you have. Oh, shit, sorry, I keep on forgetting that I have things to say. Yeah, in particular, something that will be important, given the motivations I gave, is that this kind of formalism allow you also to couple Goldstino and matter to curve space-time. So it allows you to describe cosmology, for instance. It does not require that the unbroken symmetries are really Poincaré. There could be the theater symmetries. That could be, yeah. It doesn't really matter. What matters is that you have formalism with broken fields, broken generators to which you associate fields. But any kind of matter can be coupled to it. In particular, the metric can be coupled to it. And of course, you pay a price, right? You don't have the proper supersymmetry where you have full multiplet. So this thing cannot be a UV complete theory of supersymmetry. And in particular, the formulation is such that it comes with a natural cutoff. So around energies given by the square root of this parameter f that I presented, the theory loses its predictability, and you have to go to the full UV completion where supersymmetry is restored, and you see the full structure in multiplets, etc. So the existence of that cutoff, we can see from the formula I was writing down. Sorry, for instance, if you look at this theory here of the Goldstino, you see that it has self-interactions, which are higher dimensional operators. They're not they're irrelevant operators. They're effective operators, which are suppressed by some powers of the scale f. So naturally, the amplitudes that are generated by this Lagrangian at some point break perturbative unitarity, for instance, and you hit the cutoff, the natural cutoff of your theory. So yeah, all of these theories should be understood as effective field theories, valid up to a scale which is at most roughly the scale where supersymmetry is broken. Okay.
So
maybe
if I make the limit from the some UV completed formulation to the IR where the CCWZ is working, has been applied.
Yeah.
I'm always sure that in that decoupling limit, in that limit, I will obtain always the same results that the with the invariants that I've constructed with
No, well,
system.
no. So if you do, let's say, a naive matching, so you just like diagonalize your mice matrix, check what's heavy, what's not, you integrate what's heavy, and etc. You rely on a theory that doesn't exactly that doesn't really look like what I just said.
Mm.
So to land on what I just said, you should perform a set of like standardized transformation that have been worked out in this paper, for instance. So CCWZ, for instance, they give you the set of manipulations you should perform if you want to exactly match the picture. So in principle, if you just do it naively and you just keep the fields that come out naturally of your UV model, they're not going to be, like the Gostino won't be exactly that object, it will be something else. But there is a filter definition that brings the thing you just built to this thing. Yeah, that is always possible.
If I do the manipulation of the matching at the level of amplitudes, in principle,
Oh, good.
I
Sure.
I should find the same, no?
Absolutely, yeah. The level of amplitudes, the answer. Yeah, this is the most general EFT of any theory that breaks supersymmetry. So as long as you're writing amplitudes that make sense in this EFT, so as long as the energy is sufficiently low, there's nothing you cannot reproduce. There's nothing that this framework cannot reproduce. Yeah, this framework is the most generic thing.
Course,
Like any.
Of course, I must be sure that the most general invariants that I can construct, but by CCWZ has been taken into account. Otherwise,
Absolutely. Yeah, no, of course. Yeah. Oh, yeah. It's well, yeah, but that applies to any kind of effectivity theory, right? You have to write the most general thing that is allowed by symmetries, and indeed, yeah, if you start being picky about which operators you write, you're gonna run into problem, which is something I'm gonna mention not in this formulation, but in the other formulation. So yeah, with these ideas in mind, some of the things I'm gonna say later will sound very trivial, but that's good. It's better this way, I guess. Yeah, but no, absolutely. Yeah, you need to include everything that you should include or that can be included. Yeah.
okay, yes.
Good. Okay, so that's my option one, the most generic option. And now I wanted to talk about what I'll be actually discussing, which is the option two. Well, out of probably other options, but those are the two options I'm gonna present. And the second ID uses what we call constrained superfields. But let me first describe constrained fields in general. So here the idea is, instead of using the Goldstone bosons, you can think like take more of a UV picture and impose constraints on full multiplets, so something that would be a UV multiplet, to remove some of the degrees of freedom that you assume are just got heavy around the energies where the symmetry is broken. So let me, yeah. So this, I'll give you an example in a second. Let me just say that this logic is a bit more adapted when you have in mind, for instance, couplings between the Goldstone bosons, two sectors which remain like almost arranged in multiplets. So if you have, let's say, a sector that like feels very weakly the breaking of the symmetry, and you want to couple it to the Goldstone bosons, for instance, you have like this mixed these sectors with mixed nature, the one that are still multiplets, the one that are not, and these kind of constraint fields allow you to couple them very simply in a way that is a bit closer to the UV formulation of the theory. Let me give you an example. So still in the case of this ON to ON minus 1 spontaneous breaking, if you make the assumption that there exists a fundamental representation in the UV, that is the one that breaks the symmetry in this way, then you can choose to parameterize the fact that the symmetry is broken by imposing this kind of condition on the fundamental representation itself. So this would be your proxy for the field that breaks the symmetry, and the fact that so you have a radial mode, some kind of Higgs mode, but when you leave at much,
we are not seeing. Okay,
oh,
just
damn.
now we see the condition. Okay, yeah.
Sorry about that. Can you see the orange box now?
Yes. Now we can see.
Okay, sorry. I hope that does not happen too much. Otherwise, it's going to be hard for you to follow. But let's. Okay, sorry. That's the problem with all the overlays. I did not anticipate this, but Yeah, sorry. So that's what I was discussing later. Yeah, so you assume that there is a fundamental representation in deep UV that breaks your symmetry, and in the deep IR, like the radial mode, for instance, the Higgs mode that parameterizes the fluctuation of this VEV, for instance, is extremely heavy. So you can like it's basically frozen, or at least you can integrate it out. So the rest, the things that would be light are all the modes that remain active when you impose that constraint. So that constraint basically tells us that the Higgs mode is fixed and the rest is still allowed to fluctuate. And this, of course, is in one-to-one correspondence with the other pictures, namely a field that has that respects this constraint can be put in that form, can be put in the form that we saw before, where you factor out the VEV and the different directions, the different fields can be like mapped to the coset, to the coordinates of the coset. So there's like a one-to-one correspondence, but you can phrase it as a constraint rather than using the direction of the coset as fundamental parameters. When you do this, it's a bit simpler to build Lagrangians. Namely, this object still behaves as a proper representation of ON. Simply, it is constrained by that equation. But what you can do is use the full UV Lagrangian, the one that has like the very simple ON invariance. So this could be a full ON. This is a full ON multiplet. This is a full ON multiplet. Simply, the fact that you describe the low energy theory is encoded in this constraint. So that's another way of going about it. So this matter field may or may not be constrained, depending on whether it's split because of the component of this multiplet are split because of the breaking of the symmetry, or they may not be if they like, let's say, couple very weakly to the source of breaking. So they don't have to be constrained, but they also may be constrained in order to account for that fact. So that's something that we also there's a systematic correspondence with the two, but this one has the advantage that you can like recycle your UV Lagrangian that you're maybe more used to building, and turn them into Lagrangian that encode the effective dynamics of constant bosons. So again, the same can be applied to supersymmetry breaking, and instead of constrained fields, now we deal with constrained superfields. So this thing was, I think, pioneered by Rocek in the late 70s, and it's been revived by this paper of Komar-Gotsky and Seiberg, and many more that followed. I'll be discussing the formalism introduced by these guys, by Komar-Gotsky and Seiberg. Okay, so constrained superfields. What are they? So what Komar-Gotsky and Seiberg argued and showed is that there's always a way of finding a chiral superfield.
We don't see the slides of constrained superfield.
What about now? Yeah, sorry. What is maybe I should. Okay, let me try. Let me try to get closer to my Wi-Fi. Maybe that's the reason. Let's see. Sorry. Can you see them now? Or?
Now, option 2, constrained superfield. Okay.
Oh, really? Oh, yeah. Sorry. Can you?
But not any formula.
Okay, I'm trying to get closer to that to my Wi-Fi in case that's the reason. Sorry. Usually that I've never had the issue of that sort. Sorry. What can you see now? Can you see something? Or?
No, the same. Option 2, constrained superfield. And we see the yellow box with ON to ON minus 1.
Okay, so I have no idea why it's doing this. What can you see? Okay, now you see what I see. Very good. Can you see this slide now?
Okay, does it appear? Now we see the Komar-Gotsky Seiberg.
Okay, very good. Okay, so sorry, I don't know what's going on, but yeah, good. So yeah, sorry. So let me go back a second. Okay, I was discussing this ON thing, and I was telling you guys that this can be applied to Brocken supersymmetry, suggesting the notion of constrained superfields. And I'll be discussing the formalism introduced by Komar-Gotsky and Seiberg. Yeah, so what Komar-Gotsky and Seiberg argued is that in any theory of Brocken supersymmetry, you can build a chiral superfield that may not be an object that is fundamental in the theory. It may not match to a chiral superfield in your UV Lagrangian, but it's an object you can build, an object that could be composite, for instance, but it's an object you can build. And the fact that supersymmetry is broken is encoded is encoded in this condition here. So you can build an object out of the field that has non-trivial dynamics, but that satisfies the superfield constraint. So that's the basic premise of the construction of Komarkovsky-Seiberg. So here we
don't see the
sorry?
We don't see the constraint.
You don't see the blue box?
No.
Come on. What's going on? Okay. If I don't, okay. Okay. Now there's the blue box in principle. Very good. Okay. Let me assume you see the blue box. So that's the superfield constraint I was talking about. So that's the basic building block for this construction of Komarkovsky-Seiberg.
And actually, I must say that this constraint was also used by Casalbuoni.
That's right.
De Curtis, Ferruglio, Gatto.
That's right.
All the stuff.
Yeah, actually, I think the first hopefully you can see my slides here, but the first paper that did it that I know of is this paper of 78 by Rocek, and indeed some others came later. I think that's the paper. I think that's the earliest.
I know that group. That's why I was.
No, but I agree with you. There were other papers in
1987, 88. I mean,
right.
solving this constraint in the UV.
No, I agree with that. Yeah, sorry, I didn't mean that they invented it. I just meant that these guys revived the use of that constraint, okay. And I think they made this. So they did several things. I think they first, argued why they gave an argument for why it's some kind of a universal object.
Mm-hmm.
And I think then something else that they did is to think like very systematically about how you can couple it to matter. So I think they pushed the reasoning behind it a bit further. But indeed, they were not the first one to write that equation. That's absolutely right. But their paper kind of revived that whole literature. And yeah, this is a superfield constraint. So it's not x squared equals 0 does not imply that x is 0. So in principle here, there's an equation below the blue box that shows that if you expand that superfield in components, this x squared equals 0 constraint actually does not, simply amounts to the fact that this scalar component of the superfield is not a fundamental field anymore. It's just a composite of fermions. So basically, this constraint removes 1 degree of freedom from the superfields. It removes the scalar and only leaves the fermion. So this one is an auxiliary field. It's not a physical degree of freedom. And so this is exactly the kind of things that we associate with the Goldstone multiplet. Just one fermion that has proper transformation of supersymmetry that only depends on itself. And this interpretation is of course consistent because to solve that equation in a way, to get that result, you need to assume that the auxiliary field is non-zero. And when an auxiliary field is non-zero, that's a symptom of supersymmetry breaking. So this whole picture is consistent. If supersymmetry is broken, then you can solve that constraint, and then you get a multiplet that only has a fermion that you can interpret as a Goldstone multiplet.
And the small f is the verb of the capital F?
Yeah, that's right. The thing that I used to call small f before is the value, like the value, the background value of this thing. So the vacuum expectation value of this thing. Absolutely. Yeah. And to see why that might be a simpler picture than the one of Volkov-Akulev, the one of CCWZ, you can think about the most general Lagrangian that you can write for that object. And it's actually very simple. So since x squared is 0, you can put at least one x and one x bar. That's the only thing you can do. So the Lagrangian, the most general Lagrangian with up to two derivatives in the field is this. So it's extremely simple, and the little f here is the little f that we had before. And it happens that when you write this Lagrangian, you write the equation of motion. You put this auxiliary field on shell, and you just write the theory of the Goldstino that results. You land exactly on Volkov-Akulov, up to a field redefinition, but you land on the same dynamics. Very good. And what Komarkovsky and Seiberg further proposed is that how you should couple these things to matter. So there are different ways of doing it, depending on how.
Well, wait a minute. When you say on shell, because we don't see the The formulas. When you say on shell, no, okay, that's not. You refer to the fact that you solve the equation of motion for F.
Right. Yes. Yes. So this thing is it's an auxiliary field. So its equation of motion allows to like determine it completely. Right. It's not a propagating equation.
Yeah.
So you can solve it and write f is of some function of the Gauss-Tino. You plug it back and you get a Lagrangian of just the Gauss-Tino, and that Lagrangian you're getting is has the same dynamics as the Volkov-Akulov Lagrangian. It does not exactly look like the Volkov-Akulov Lagrangian because you have to perform some field definition to match the two, but yeah, the on-shell amplitudes would be the same, for instance. Yeah. So okay, yeah, yeah. So yeah, I'll try to stay. I'm not sure whether it helps or not. I'll stop the full screen mode. I don't know if that's the reason. Probably not. But let me try like this to see if it helps. So yeah, here in principle at the bottom of the slide, I'm discussing the couplings to matter. So those depend a bit on the kind of matter you have in mind. So if you have something that is almost supersymmetric, so something that still at low energies looks like a full multiplet with like very mild differences because of supersymmetry breaking, you can use a normal Lagrangian, a normal supersymmetric Lagrangian, and then the couplings of X to the matter would implement soft breaking. So for instance, something like this, which would couple this X Gauss-Tino superfield to some random chiral superfield, this thing would in particular create soft scalar masses for the scalar component of this. So it would give mass to the scalar and not to the fermions, with the scaling that is this in terms of that cutoff that I just introduced. Okay. So that's one. So if you want to like see, like resolve the appearance of the soft masses, because they're much lower than square root of f, so you can describe them in the EFT. Then that's just the couplings to X will very naturally recreate all the soft breaking you can think of. The gauge masses, the train linear terms that you may find in the MSSM, for instance. All of these things can arise from the coupling with X. But sometimes the soft masses don't have a reason to be much lower than square root of f. So if some of the superpartners get a mass that is similar to the scale of supersymmetry breaking, then the description you need to use in the IR is a description that does not use a full multiplet. So in that case, even matter has to be constrained. So you have to use constrained matter superfields to describe the fact that some of the components of a given multiplet is missing in the IR. And this you can do with X. So here I'll just change slides in principle. Hopefully you can see. So you can use X to implement those matter constraints. So let's probably an example is simpler. So if you want to describe the fact that some scalar got a soft mass at the order of square root of f and it's not present anymore in the IR, so you need to find a constraint that removes the scalar from the degrees of freedom in the given superfield. And that simple constraints will do the job. So this can also be solved as a constraint as a superfield constraint now. So it's not trivial. It's not implying that one of the two is zero, but it implies that this chiral superfield has the following kind of expansion. So the fermion in that field is still present. The auxiliary field in that field is still present, but the scalar is just a function of everything. It's a function of the scalar, of the fermion, sorry, the two auxiliary fields in the chiral superfield and in the Gauss-Tino superfield, and it's a function of the Gauss-Tino itself. But so that kind of constraints really implement what you wanted to implement, namely it removes the scalar, and it's a way of encoding that the scalar has got a mass at scales around the supersymmetry breaking scale. And very much in the same way as we discussed that you could plug those expressions directly into the UV Lagrangian in the ON model, the same can be done here. You can just take the regular SUSY Lagrangian, plug the solution to the constraints in and get an EFT that is an EFT of spontaneous supersymmetry breaking. And these matter constraints have been
I'm always sure that by integrating out the super partners, I will arrive always to the same action that you obtain plugging the solution of the constraint.
No, you don't. And actually, that's a point. I'm gonna go back to that. Yeah, no,
Okay.
absolutely. You don't know. You hope. So this formalism was a formalism so these kind of things were not addressed in the original formalism, and I think that probably was a. So there are ways of making the two. So it depends. So the logic is very simple. If you're used to EFTs, the idea is that if you are very careful about what the cutoff is and what you should include, if you want to include all operators, then the two will match. But these kind of constraints have been used in literature in a way that was maybe too naive, if I can say. Namely, they were taken, as you said, they were taken to be sufficient to encode all the effects associated with integrating out. In some cases, it works. In some cases, it doesn't. And I'll tell you an example where it doesn't.
So, and if it is so, why I don't trust much more in integrating out?
Oh, yes, sure, you could. But if you want to integrate something out, you have this thing in principle allows you to have some kind of mixed knowledge about the full theory, right? So you could be saying, okay, let me assume that in the full theory I have two Caro superfields. Okay, sure.
Mm-hmm.
And I assume that the supersymmetry breaking is such that the scalar gets a mass. Okay. Then I'm using this formalism that I hope is describing this kind of generic situations. So you don't have to tell me what is the supersymmetry breaking potentials, what are the fields, blah, 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 right? So you can just make those kind of broad assumptions, and hopefully this formalism will be sufficient to describe any kind of model that falls into this category. So in principle, it can like describe many models at once, right? It's still some kind of effective approach. If you integrate out, right, you have to start from somewhere, so you have to know your full theory.
But so maybe I don't understand. But also, if I plug the constraint, I should know exactly where I plug the constraint. So I should know exactly
sure.
What are the details of the UV completion.
No, sorry. Yeah, good. I see what you mean. So here when I say to be plugged into, I mean to be plugged into the most general Lagrangian that you would build if those things were just normal superfields. It doesn't have to be the Lagrangian of some given UV theory in which those two fields exist. The claim is that you can build this Lagrangian using the normal rules for building superfields, and just you plug the constraint in. But it doesn't have to be the UV Lagrangian. So in principle, it will have less fields, for instance. There could be superfields that are completely integrated out at scale square root of f, in which case they should not show up in this thing, but they should still show up when you want to integrate out the full UV model.
So I can start from a general Kähler potential.
That's right.
General scalar part and plug inside the solution of the constraint.
That's right. That's right. That's the philosophy here. What is much simpler than the other thing is that you can still use those rules. You can still think about the Kähler potential and superpotential. If you think back about the thing, if you think again about the thing I was saying about the CCWZ prescription. So in that slide here, I was saying that you have this complicated Gaussian transformation, this complicated matter transformation, and the way you build the Lagrangian involves nothing like a Kähler potential or superpotential. It involves regular function and some specific contractions, etc. So it doesn't really match with your usual understanding of a supersymmetric model. Whereas here, you're really using a notion of Kähler potential, superpotential. You're just evaluating those objects based on those constraints. Yeah.
But if from the more general Lagrangian with general Kähler potential and scalar potential, I make I integrate out the superfield, the super partners. I should find something that maybe by field redefinition or maybe by other stuff should be matched with the plugging inside the constraint.
Right. Yeah, that's the hope. But actually, it does not. It happens. It does not always happen. And one of the points that I'll try to convey is that it does not always happen. Yeah, that's one of the issues. It happens. So for instance, for that case, it happens always. So if you want to integrate out the scalar, there's always a procedure where this would work. But it does not quite. It depends on the constraint that you're trying to impose. But so for that thing, it works. Yeah.
If it does not happen, it's because I choose the bad constraint, or what?
Absolutely. Yeah. Yes. Yes. In one word, yes. Yeah. That's one of the messages I wanted to convey a bit later. Yeah. Sorry, I'm noticing that the time already is very late. Can I?
Sorry.
How much? Now, how much time? How much time do I have?
No, I mean, in principle, until you have energy, but
Oh, okay. Very good. Okay. Let's
no,
do that.
until
Oh, very good.
when,
No, no. It was more for you. I don't know if some of
no,
you
no,
have to
for
leave or
us,
something.
I mean, we can.
Okay. Let me go on then. Good. Yeah. Yeah. I'll in principle at the end of the talk I'll have addressed at least some of those questions. Yeah. Good.
Okay.
Yeah. So this way of thinking about constraints was very heavily used in the literature, like in the mid 2010. In principle, in particular in cosmology, because it allowed people to build simple models of inflation that have, for instance, no inflatino or no syncflaton. So ways of getting of having like just an inflaton model within a supersymmetric formulation, something that has a killer potential or superpotential. So that has been used a lot to build inflation models in supersymmetry, in supergravity, sorry. But there is a problem, yeah, which we already slightly discussed, which is which constraints should I choose? Are there several constraints? If there are several constraints, are there good ones and bad ones? How can I choose? And it's for instance, an example that shows that very simply is like very simply is the case where you want to decouple a fermion from a chiral multiplet. So now the picture is different. You imagine that you break supersymmetry at some scale, and the fermion is the one that gets heavy, and the scalar is the one that remains light. So you want to write a constraint that removes the fermion and not the scalar. So in the original Komarski paper, they proposed that constraint. So that constraint is doing that job. Namely, it removes from the chiral superfield the fermion and leaves as a dynamical degree of freedom only the scalar. But at the same time, it also did something that was removing the auxiliary field. So you may say, yeah, sure, why not? Auxiliary fields are not dynamical anyway, so the propagating states I'm describing are the same with or without this auxiliary field. So why not? Okay. Another version of that constraint that was proposed in this later paper here is this one here that you see at the bottom of this blue box. Hopefully you can see my slides. And it's doing the same job at the level of the propagating states, but technically it left the auxiliary field behind. So solving this condition would dictate that the fermion is a function of the Goldstino, that thing, and the auxiliary field of the Goldstino, but would leave these two scalar and auxiliary field untouched, whereas this constraint here at the top would transform this and this in functions of all the rest, so of the scalar, the Goldstino, and the big F of the Goldstino. So okay, in terms of degrees of freedom,
So do you mean that in this case the auxiliary field cannot be solved by the equation of motion?
It's not that it's not solved, it's just that it's not there anymore. It's just it's fully specific. The constraint gives you the value and not the equation of motion. Yeah, if you want, yeah. Yeah, there's no field to even solve for. It's not there anymore. So those two things seem equivalent because they leave the same physical modes behind. But however, I mean, you have to be careful on how you treat them, because those two constraints have effects if you use them too naive. Like choosing one or the other has physical effects if you use them too naively. So for instance, if you use either of these constraints in the same Lagrangian, so you write Lagrangians for this phi and for this x, and you plug in the result of solving the constraint, you, for instance, will get different scalar potential, which is probably obvious to those of you who know supersymmetry, because you're changing the auxiliary field content, and those objects are the source of the scalar potential. So for instance, if you want those two things to describe the same kind of physics, they should be used with different Lagrangians to reach the same result. Of course, the question becomes how, like, let's say you use this one for a given Lagrangian to get the same results, which Lagrangian should you use for this one? It's not obvious. It was not explained in any of those papers before. And in particular, there seems to be like very serious issues if you're not careful with the Lagrangian you're using depending on the constraint you're choosing. And in particular, it was shown in the papers I referenced in the motivation section of that talk, that precisely the issue of causality, so for instance, the fact that you have gravitino superluminal propagation, was associated with the use of that constraint here in cosmological spacetimes. So those papers that I mentioned in the introduction that were finding like forbidden behaviors for gravitinos always use that kind of a constraint, in particular constraints that remove the auxiliary field from the spectrum. From the spectrum of fields, not the spectrum, from the fields that define your field theory. So it suggested to us that this kind of constraint, the one that remove more than they should remove, in a sense, could create problem and should be used with very specific Lagrangians that remove the problems. But of course, the question is, how do you find those Lagrangians? And we wanted to understand this. And
but in the case of the breakdown of causality, I mean, it breaks down the causality for any choice of the parameters. Or?
No, yeah, I'll show you the parameters that work and don't work.
Okay.
Yeah.
So somehow,
if
one identifies the right parameter, one can ask the way to guess what is the UV completion, the right UV completion, and the corresponding right IR limit, or what?
In principle, yes. Although, yeah, good. So, yeah. So there are some kind of problems that you avoid if you like just restrict yourself to the good parameter space. However, I cannot promise that there are no other problems that were not found yet. So, for instance, in a couple of slides, I'll be discussing these positivity bounds, and I'll be using the simplest of them. And there are, in principle, infinitely many of those. And I don't know if all of those positivity bounds, for instance, would be equivalent to the simplest ones. But indeed, like from the simplest analysis, so the simplest positivity bounds that I'll be discussing in a second, and for this idea of gravitino superluminality, you get some constraint, and you could imagine just closing your eyes and living in the part of parameter space where this constraint is satisfied. Yeah, you could do that, yeah. But I'll try to argue in a couple of slides that we've not found that very satisfactory. But yeah, I think that's something you could say. Good. So yeah, and as you were anticipating some time ago, when we wanted to understand these kind of things better, and to simplify our life, we used this equivalence theorem that states that well, first of all, sorry, we noticed, or at least we took from those papers, the fact that this superluminality issue was associated with the longitudinal mode of the gravitino. So it was present in the equation of motion of the longitudinal mode. And so this longitudinal mode, we know that at high energies, it can be probed with a much simpler EFT than the one of the gravitino, the one that describes the full gravitino. We can just look at the Gauss-Tino equivalent EFTs in just flat space. So what we're going to do is not consider this thing in full supergravity, as was done in those papers that found these issues about gravitational propagation. We're just going to look at those constraints in a flat space Gauss-Tino EFT that hopefully is sufficient to diagnose issues associated with the longitudinal mode of gravitinos. And as we will see, it's the case. But yeah, that was our working assumption at first. And yeah, maybe let me skip that because it's not very relevant for my story. Okay, so let's see what those positivity bounds have to tell us about this nonlinear supersymmetry and this kind of issues associated with which constraint you should choose to describe gravitinos. Gravitinos coupled to matter. So okay, so so far I was mentioning causality issues, and now I'm switching to another world, positivity. So maybe let me recall first of all that causality and positivity are related. So here you should see a slide with just a yellow bar at the top. So tell me if it's not the case.
Yes.
Good. So yeah, so causality issues in EFTs have been known for some time. Probably they were known much earlier to people in the 60s doing the S-matrix program, but for us young physicists, it was revived by this paper in 2006. Yeah, so causality issues in EFTs are related to positivity issues, and let me tell you what I mean by positivity. So positivity is a notion that applies for EFT that should hold for EFTs which have a UV completion that is local, causal, unitary, and Lorentz invariant. So basically, if you have a well-behaved UV completion in the sense of what we call a well-behaved field theory, or something close enough to field theory, this kind of condition also applies to string theories. The EFTs that should arise from this kind of V-completion should have a notion called positivity. So let me know what that is. Let me tell you what that is. So positivity is something you see in scattering amplitudes. So the simplest of them, the one we understand the most, is the one associated with the 2 scattering amplitude in the so-called forward limit. Forward limit, namely, is the thing where the T parameter, so you take the amplitude and you go to the limit where the T parameter is 0. So the T Mandelstam variable is 0. And the one that we really understand is the one where two states are the same, where like you have like state 1 to state 1 and state 2 to state 2. So those would be the scattering amplitudes we understand, for which we understand the best the positivity. And positive rises in the following way. So because of those constraints on the UV completion, you can use complex analysis. You can use, so those kind of assumptions have can be rephrased in the amplitude language as analytic and convergence properties of the amplitude, etc., that allow you, for instance, to use complex analysis and turn the amplitude into some kind of contour integral of the amplitude expressed into a complexified Mandelstam variable. So you think about this S is usually like it's the energy, right? It's a real number, but the amplitude can be uplifted to the full complex plane when this Mandelstam variable S takes all possible complex values. So that's an object you're allowed to think about. In that case, it is also known that object is analytic almost everywhere. So it's analytic except in the places where you have singularities associated with physical particles kicking in. So in particular, for a theory that has a gap, for instance, you expect no singularities except on these kind of parts of the real axis. So on all the rest, the amplitude is analytic. So for instance, you can get the amplitude by just computing this kind of contour integral on that blue circle here. That will give you the amplitude evaluated at the pole that you just like artificially introduced here. So you can play these kind of games. Now you have complex analysis. First thing, Here, you can, if you're computing this blue contour for a very small contour, very close to 0, then the energy is much lower than the cutoff of your EFT. So the full UV completion is very well approximated by the EFT, and you can compute the object here using the EFT. Okay, so that contour here, the result of this complex, this integral is related to EFT coefficients. But okay, now you think about the full UV completion. So this amplitude in the EFT is just the approximation of the full answer. So now in the full answer, you should be able to deform this small circle using complex analysis into a much larger circle until you lose the contour at infinity and you're only selecting the thing that happens along those poles. So here I've been a bit sketchy because the thing you really do in positivity is something where you have slightly higher powers of S here, because the big circle would not decouple for this very simple thing, but let me not enter into details. I'll try it. Yeah, in principle, you should be a cube here, and this thing is not really the amplitude that you're picking up. It's the expansion at order S squared of the amplitude. But let me not write those formulas.
And you're supposing that your A of S prime has been already subtracted.
Exactly. Yeah. Exactly. Yeah. So through this kind of deformation of the contour, you can map a small contour to this kind of contours. And at that stage here, this kind of contours can be related to the cross-section through the optical theorem. And here, this one can be related to this one through crossing symmetry. So in particular, you can relate everything to this contour here that relates to the cross-section through the optical theorem, and the cross-section is by definition a positive quantity. So this thing here that was a small circle, just some expression in EFT coefficients, can be related to something that is positive. So that's how you see positivity arising in EFTs. So basically, I'm not going to give you explicit examples. I'm just going to give you results. But this positivity shows up in EFTs as a statement on Wilson coefficients of the form that combination of Wilson coefficients should be positive. So that's how it shows up. And for the case of interest here, we will look at specific 2-to-2 scattering amplitudes, which are the following ones. So either for a scattering amplitude of 4 Goldstinos, or a scattering amplitude of 2 Goldstinos and 2 fields. Here that would be scalar, because I'll be focusing on theories where the fermion superpartner decoupled and the scalar remained. So this could be the inflaton, for instance, for those people who were coupling the goals, who were coupling the inflatons to constraint superfield. So those would be the two kind of amplitudes that matter, and those kind of amplitudes have been very much analyzed in the literature, starting from that, to my knowledge, starting from that paper of Brando-Bellezzini. So we just took the results from the literature and just rewrote the results that were worked out for any kind of theory of EFT, of fermions and scalars. So we just applied them to our case of theories that have nonlinear supersymmetry. So let me show you
this amplitude has been computed with some specific constraint.
No, so what these people did was to take any EFT of one fermion, let's say, any Wilson operator, and just they worked out all the possible positivity bounds. So that is more general than what we are interested in. So what we're going to do is take those results and just replace all the Wilson coefficients by the ones that are predicted by nonlinear supersymmetry. Same here. Yeah. But no, these people have done more work that is needed for us. Namely, they did the most general case without any without any symmetry assumptions, without any supersymmetry assumption, and we're just going to recycle and apply those results to our specific case. Yeah.
Okay.
So let's see what that gives. So let me give you. Let's look at the case of that constraint here. So for that constraint here, let's just look at what positivity tells us for that constraint. So I'm not going to show it, but in our paper, we also analyzed other kind of constraints. So for instance, there are constraints that remove not only the fermion, the auxiliary field, but also part of the scalar. So this would be the kind of constraint that gives you one real scalar that people have been using for inflation. But I mean, the story is identical, so let me focus on that story here instead, because we've been discussing it already. Okay, so in that case, you can write some Lagrangian, and you realized by using the constraint on X and the constraint on that field that the most generic Kähler potential and the most generic super potential have the following form. So it's any function for phi, because this constraint is not very constraining in a sense. So any polynomial of phi, for instance, is still allowed and is in principle is independent of other polynomials. So you can use any Kähler potential here, so you can use any function here and any function here, except that it has to be real to form a Kähler potential. And here, any holomorphic function to form the superpotential. So you take this, you plug in the constraint, you expand in fields, you work out your Wilson coefficients, and you compare with the positivity bounds that were obtained on the most general theory of a scalar coupled to a Goldstino, or actually to a fermion, and you apply it to our case of the Goldstino and the inflaton. And you get the following positivity bounds. So the result of those positivity bounds would be this thing.
So, but you must compute the amplitudes also in this Lagrangian after imposing the constraint.
Yeah, in principle, yeah. In principle, that's what you do. Yeah,
matching the coefficients.
But yeah, but those yeah. So sure, yeah, you could do that. However, so what we did instead, what was very simple in our case was simply to write the Lagrangian, perform some field redefinitions that matched to the basis that these guys used, and that was sufficient. That was enough. But indeed, the two things are, I mean, computing the amplitude would have been also a faster way, but well, would have been a very satisfactory way. But in our case, the Lagrangian that was spit out by the procedure was very close to the Lagrangian used in those papers. So we didn't really need to recompute amplitudes. But indeed, in principle, you should do that, absolutely.
And
but yeah, the result is this.
Level, of course, is more than enough.
Yeah, absolutely. Yeah. So the result is this, and well, first remark, it's not automatic. So there may be parts in parameter space where this is not true, and also something that was reassuring to see for us is that this was exactly the condition that people found for the gravity node to propagate at a speed that is lower than the speed of light. So indeed, we recovered in this approach that only focused on the Goldstino, the condition that was also necessary for the gravity node to propagate at a speed lower than the speed of light. So it seemed that using this equivalence theorem picture was sufficient to diagnose the issue, and it was sufficient to see where the issue would come from. Let me say that, so we also performed this kind of analysis for the other constraint that I mentioned, the one that removes the fermion but not the auxiliary field. And here instead we found something different. So we found the constraint. We found that the positivity bounds would have the form something positive has to be positive. So it was automatic. There was nothing to ensure, which is consistent with the fact that this constraint seemed to yield no causality issue when it was used in, let's say, inflation models in supergravity.
So it means that in the second constraint, for any choice of the superpotential and the Keller potential,
Absolutely.
you obtain the positivity.
Absolutely, yeah, yeah. That's what we
it means that in this case you know exactly from which UV comes your IR.
Well, not really. No, what you know is that there is at least one UV. So for this thing, you know that whatever parameter you choose for the EFT, there is one UV that can do. There is it's possible at least that some UV can do it.
Okay.
Whereas what you know here is that if you violate this identity, no UV completion could even be found. So it does not tell you what the UV is. It tells you that the UV might exist or cannot exist. Yeah. In this case, if you violate this condition, it just cannot exist. If the condition is respected, it might exist. And in that case, it might always exist. There's nothing. That's right. Good. Yeah, but so indeed, so then we started asking the question that you asked before, namely, let's say we just sit in a part of parameter space where this is okay. Should we be happy with this constraint, or are we unhappy about the fact that if we go a bit further in the parameter space, we start violating the constraint? In particular, we were confused because we use something that looks like a two-derivative UV Lagrangian, so a very well-behaved Lagrangian, and the constraint was kind of messing it up. So it seems that using the simpler Lagrangian, that in principle is associated with no issue at all in supersymmetry, is not the right procedure for this thing. So there should be a procedure that is not using that Lagrangian, that kind of removes the positivity bound and is really describing what the matching procedure should give you. So yeah, that's the question we were asking. So is there a way of removing this positivity bound? Is there a way of understanding what is missing to really have a UV completion for any kind of parameter? And and then to understand, sorry, to explore that question, we decided to match, to study matching, but to study matching, like trying to be as close as possible to this formalism of nonlinear supersymmetry. So in particular, we want to match in superfield language and not in component language. And I'll tell you how we did that. So I'll be discussing integrating out pieces of superfields. So in principle, here you see a slide with a bluish line at the top. Yeah, so long ago when we discussed CCWZ, we argued that the existence of a Goldstino was sufficient to completely break the multiplets apart. So there is no need for a multiplet structure. As soon as you have a Goldstino, using this kind of CCW-like tricks, you can really break multiplets into pieces, and there is no even meaning to it. There is no reason to think about a multiplet in the first place. So in principle, for constrained multiplets, you should be able to do the same. And actually, we found a way of doing exactly that, namely using at the level of superfield. Sorry, here it should read superfield, not multiplet. For constrained superfields, we can really do this. We can really use the existence of the Goldstino to break the multiplets into pieces and just get rid of the ones that are heavy through a procedure of matching. So let me show you how that works. What we can do is explicitly break a multiplet into pieces. So you can break, let's say that chiral multiplet, you can break into 3 pieces, one of which is constrained so that it contains only a scalar, one of which is constrained so that it contains only a fermion, and one of which is constrained so that it only contains an auxiliary field. You could, of course, choose to put some of them together and just think about 2 pieces and so on, but you can go all the way and break it into as many pieces as you like. So let me show you that it's not just wishful thinking. You can actually do it. So for instance, the formula for that guy is this. So if you want, so one formula is this. So if you want to build an object starting from the original object that is such that it's only made out of the auxiliary field, you can just evaluate that formula, and that does the job. So this thing is made out of the auxiliary field, and the rest are just functions of the Goldstino, the auxiliary field, and the auxiliary field of the Goldstino. In particular, the thing that sits at the theta equals 0 component, the thing that you would call the scalar, is just some function of the auxiliary field and the Goldstino. And here, the fact that we've been assuming the existence of a Goldstino in the first place is shown here. So for this formula to make sense, we want this quantity here where, sorry, for those of you who don't know, this big D here is this derivative in superspace. So it's basically differentiating with respect to the direction of space-time that is associated with moving in supersymmetry space. Yeah. So this is probably shocking to mathematicians what I just said, but sorry. So this is a derivative in superspace. And this thing is the superfield version of the auxiliary field of the Goldstino. So to form that object, we had to assume that, like, divided by this makes sense. Namely, we have to assume that the auxiliary field of the Goldstino is non-zero. So namely, we have to assume that this field is breaking supersymmetry. So this is consistent. Namely, if we hadn't had a Goldstino to use, we could not have done that. We could not have split the multiplets into pieces. But once we have a Goldstino, we can. So this is the formula for this field. And there are other formulas which are longer and longer for these two guys. I didn't write them down, but you can find them in our paper. And yeah, to get the constraints in the IR and to get the Lagrangian in the IR, what we can do now is just simply integrate out the pieces we want to integrate out. And so let me give you an example of what that gives. So I could have something that you can do is integrate out this guy, and you'll find that the naive picture I gave, so just a constraint that removes this, and the regular Kähler potential plus superpotential is sufficient. But some things get more complicated when you start integrating out this guy. So let me check, are you guys still here? Or? Yeah, you are. Good. Okay, I wasn't sure. So let's see. Let's try to integrate this piece out. So let's try to write a theory that doesn't have.
No, we don't see any more the slides.
Oh, sorry. What do you see now? You see my face? Or?
No, we see your face, but also the screen, the mirror of.
Oh, I'm very sorry. Sorry, I should not have checked. Can you see the slides now, or still not?
No.
Oh, damn. Sorry, should not have. Slides?
Yes.
Very good. Very good. Very good. Okay. Yeah. So I'll show you what happens if you were to try to integrate this guy out, because that's the reason. That seems to be the reason behind all the issues that people found in gravity no propagation. So let's just try to integrate out this full superfield. So it's morally the same as just putting the auxiliary field, just enforcing the equation of motion for the auxiliary field. But now we are doing it at the level of a full superfield that is built out of the Goldstino and the auxiliary field. So it's morally the same as entering that as like fixing the auxiliary field to its background value. But the fact that we do it at the superfield level will have an implication, as you will see. So let's do that. Let's write this UV Lagrangian here now. So the fields are not constraints at first. So they're not constrained, but we just integrate out the part of this that contains the auxiliary field. So what you get, I called it IR. It's not really IR because this guy is just an auxiliary field. It's not heavy in any sense, but I really mean the Lagrangian where this thing disappeared is the following. So you get what you would have naively assumed if you were to impose the constraint. So before we said just impose a constraint, just keep the same Lagrangian. So that would be this first line. That would be keeping the UV Lagrangian, but now instead of using the full field, use the field that has a constraint. In this language, that would be using the two remaining pieces out of the three you had before. But that's not what happens. So when you're careful and you're solving for you're writing the equation of motion for this superfield, and you just solve it recursively, you realize that you generate more things. So in particular, there is something that looks like, I didn't write the whole thing, it's ugly. Again, you can find it in the paper, but just to give you an example, just to give you a feeling of how it looks. Oh, sorry, I'm being, yeah, so this W, sorry, I've been sketchy. This W should be, it should be this guy here. Just this, it's the same. Oh yeah, sorry, it's the same, but in practice, it's the derivative of G here that matters. So yeah, you're kind of generating this. You're generating these kind of objects in addition to the naive thing of just plugging the constraint in the UV Lagrangian. And so this would be the naive EFT of constraint superfield, but this is some kind of non-decoupling correction. So here again, I'm using the wording of IR non-decoupling correction. It's not really appropriate for an auxiliary field, but that would be what happens If you try to integrate the part that has both the fermion and the auxiliary field, you would really think about the IR limit. And this is a correction. Actually, this is a correction that you could add. And actually, if you think about it, it's a correction that you should have added, because it's some expression that has a cutoff that is at square root of f. So you see that there is the scale by which you're dividing here is oh, sorry, I'm missing a square here. Sorry, there should be a square. Here it should be d bar square x bar, the bottom, sorry. So the thing you're dividing by here is f. So this thing is just some higher dimensional operator in superfield language with a cutoff that is square root of f. But when you're using the constraints in the first place, like the fact that there is a cutoff at square root of f at square root of f is already built in. So these kind of things are actually things that we should have included, we should have checked. They just show up. They look very weird in superfield notation, but when you think about EFTs, they should be there, because they're just hiding. They're just a way of hiding higher dimensional operators with a cutoff at square root of f. And in that case, it turns out that this piece is exactly tuned. Well, not tuned, but it's exactly the thing you needed in the first place for positivity to be automatic. So in that case, I started from some field theory that had no constraint and that had a very well-behaved Lagrangian. So I should have no issue in the when I do this manipulation, I should land on the theory that has also no issue. And indeed, the causality issue that I was finding because of the constraint in this part are exactly canceled by this part here. So when you do matching, things work perfectly well. So what's happening actually is that when you're using the constraints, even though it looks like you're not using an EFT Lagrangian here, you're using the full the full UV Lagrangian. The fact that you're using constraints automatically generates some higher dimensional operators when you're expanding this, when you're plugging the solution in this. And this thing sometimes should be corrected to be consistent by this kind of ugly beasts. And in particular, for the kind of constraints that people are using for inflation in supergravity, some of them needed this kind of correction that were definitely non-trivial at the order they were looking at. So for instance, in some cases, this thing would even change the scalar potential. So even for inflation, it's very important. Yeah.
And wait a minute. And I mean, there will be cancellation of terms which were not making automatically the positivity.
Exactly. Absolutely. Yeah.
So
you
should be able to see this cancellation not also at the level of amplitudes, for instance, at the level
yeah, sure, absolutely,
of observable. Yeah. I mean,
sure, absolutely, yeah. I've not tried it, but yes, this thing will generate contribution to the scattering, for instance, that will be exactly tuned so that it cancels the issue with positivity. Yes, absolutely. I've not tried it, but it has to be the case. Yeah.
So it is worth also to do this check to see at the level of amplitudes.
Yeah.
What?
Yeah. So yeah,
how the positivity arises after this matching. No?
Yeah. So this thing we did. I don't know if we included it in the paper or if we just checked. I forgot. But what we did was to expand this. So yeah, again, we did not compute amplitudes, but we expanded this Lagrangian to an order that is sufficient to describe two-to-two scattering at order s squared, which is what people deal with in vanilla positivity bounds. And so we wrote the Lagrangian. So we have this contact term that generates it, and we just checked that the thing that should be positive in front of it is positive. Mm-hmm. So this we checked to some extent. Yeah. I don't know if there are like more refined checks that should be performed for like a more refined version of positivity, but at least the basic one I think was checked in what we did. Yeah.
I think that's to see it at the level of amplitudes.
But yeah, definitely
would avoid the problem of field definitions, because
sure, definitely
inside of the amplitude everything is
absolutely
is invariant under the parameterization.
Sure, absolutely, yeah. Mm-hmm. Okay, so yeah, that's basically all what I wanted to say. So let me just very briefly wrap up. So there were basically two things that I was trying to say. So first of all, the positivity is shedding light on these debates that were associated with the with the issues encountered in gravitational cosmology, and in particular, it allowed us to better understand which of the constraints have like very like match to a UV origin in the simplest incarnation, and which ones needed some like refinement of the formalism. And the second thing that we saw is that this off-shell Golsino formalism allows us to navigate between superfield constraints at the Lagrangian level. So we can really see this splitting of multiplets, and we can really understand, we can really track down how we can integrate part of it once supersymmetry is broken and land on a theory that has constraint and some Lagrangian. So we could check that the scalar constraint is fine, for instance. We could check that the constraint that remove the auxiliary fields are probably not fine, things like this. Okay, and I'll stop here. Okay. Thanks for listening.
Oh, thank you so much. Really amazing.
Yeah, I'm very sorry for the technical problems.
Yeah.
Yeah.
So there are questions now for Quentin. So there is one hand. I cannot see which is one. Christian, please.
Hello, thank you so much for the
Hi.
talk. I have some questions. I didn't understand the meaning of chiral superfield.
Oh, good. Yeah. So I'm very sorry. Yeah. Sorry. I designed that talk for people who know a bit of supersymmetry. So I'm very sorry for those of you who didn't really know this. But let me see. Where did I say that? Sorry, I'm going back to it. Yeah. Good. So chiral superfield is just a it's so in 4D supersymmetry, right? You have two kind of multiplets when you deal with the flat space supersymmetry, so no gravity. You have two kind of multiplets. So you have multiplets which have spin 0 and spin 1/2, and multiplets which have spin 1/2 and spin 1. And the ones that have spin 0 and spin 1/2 are described. So so you have states states which are spin 0 and states which are spin 1/2, and the chiral superfield is a convenient packaging of those states, of the fields that describe those states. So it's a superfield that has a scalar, a fermion, and some auxiliary field. So in superspace, it looks like this. So this kind of notation I'm showing now. So this theta is this kind of new coordinates that we call that define what we call superspace. And this is the chiral superfield. So it has a scalar, a fermion, and some other thing that looks like a scalar, but actually does not have a propagating equation of motion. So its equation of motion is not of the form box F equals something, it's of the form F equals something. So this is really something that has a scalar and a fermion in it. But sorry, that's supersymmetric. This is supersymmetric like language. Yeah.
Okay, I have another question. Is
Please,
it
yeah.
possible to define chiral currents or find chiral anomalies related to that superfields?
Oh, good. So let's see. Right. So this field only has a Weil fermion in it. So if you give it, I mean, if you start charging that field, you definitely have to check for chiral anomalies. Yeah. And there's probably a way of writing that in a superfield way. I've never thought about it, but I think so. Yeah. But there is, yeah, for the perspective of chiral anomalies, I don't think that, yeah, I don't know. I've not thought about this too deeply, so maybe I should not comment too much. But
No, I mean, the chiral superfield is a specific, irreducible representation of the Poincare superalgebra.
That's right.
And I mean, the same as we do in usual, without supersymmetry, the D1 0, D0 1 are implemented in constraint, which select from the mass of the possible expansion of a superfield some irreducible representation.
Right.
And to select chiral or antichiral, it is the same D1 half 0 and D0 1 half, the same that we do in Minkowski space. Yes.
Okay,
More
thank you so
questions?
much.
Yeah, okay.
Yeah, sorry. Yeah, thank you. I hope I answered
More
the question.
question for Kenton? Edison?
I have a question that is a bit off topic,
Please.
but I was wondering how does the spontaneous breaking of nonlinear supersymmetry affect the mass spectrum of particles in phenomenological models?
Oh, well, no, yeah, sorry. So maybe I misunderstood the question, but so nonlinear supersymmetry is really just a framework that you can use to describe any theory. Well, sorry, it's a framework that applies to any theory that has broken supersymmetry. So it doesn't say anything, right? It's not predictive in the sense that any UV completion of the soft terms of the MSSM, for instance, would be embedded in nonlinear can be described using nonlinear supersymmetry. So it's a framework to describe those things. In particular, it's the framework that allows you to understand the couplings of matter to gravitinos or Gorstinos, but it doesn't say anything about the precise model behind it. So like, it doesn't select among the SUSY breaking models or things like this. It's just a way of like keeping track of the supersymmetry that was broken in the IR and keep track of the consequences of the fact that there was once a supersymmetry that was broken.
Okay, I see. Thank you.
Sure, thanks for the question.
And I mean, in this case, the couplings of the Gostino to particle of the standard model can be constrained by the positivity bounds to
Absolutely, yeah.
to have a better model that.
Sure, yeah.
If one day supersymmetry will appear, I mean, somehow we should have a way to recognize it. I mean, the positivity bounds would provide a way to say how strong is the coupling. So
no, I think let's see. No, I think I don't think it would help. Like if you measured something that you interpret as a Goldstino, for instance, I think it gives you information. Okay, there are two things. So in our case, it was a tool to better understand the formalism and better understand what should be used and what should not be used as a formalism. Now if you think in terms of phenomenology, I think that just the only thing I'm aware of is that what's interesting about positivity bounds is if they are broken, because if they are violated, then you understand that something very fundamental is happening, because if you made the kind of mild assumptions that the physics in the UV is basically behaving like physics you've already seen. So if that is true, then positivity bounds should hold. So if positivity bounds do not hold, then it suggests that the thing in the deep UV is much different from what you're used to. But if the positivity bound is satisfied, you just don't learn much. You're just like, sure, okay, could be anything. Could be something I know, could be something I don't know. So yeah, I think it would be much more interesting to see the violation of those bounds. But okay.
What I asked was, I mean, so you said that there are two constraints. One in which the positivity bounds are automatically, the other not.
Yes.
And I mean, by the technique of the matching, one is able to improve the bad constraint in order to get better access to the UV.
Yeah, to some extent, yes, but the issue is that So yeah, so the matching showed us that we were definitely missing a piece, and that explained why the constraint alone, well, yeah, it was showing us, it was suggesting how we could fix the problem if we really wanted to keep that constraint. But the issue is that, okay, we've done matching, but the idea is still to be able to do some bottom-up analysis. So you would like to have a formalism that you trust, for which you can really do the naive thing, and you think and you hope that it will work. So the matching story, I think we would rather use it as a motivation to say that constraint is probably too complicated to use bottom-up because you're missing some pieces if you use the naive Lagrangian. So either you match, so basically if you don't know what to add, if you just have to match each time to get the right result, then you're not really doing a good bottom-up approach. Of course, that's not completely true. It also showed us that there are some things you would not write that you should write. It's part of your EFT, and it's going to be useful to fix the problem. So you can take it two ways. You can take it as a suggestion of what you're allowed to write in order to fix the issues if you find some issues. Or second, you can see it as a way of arguing that you should focus on the constraints for which at least we've not seen those issues. Because they're at least probably closer to a case that for which the behavior is very naive. Yeah, that's what I would say. Yeah, because we've done, at least, yeah, for instance, we worked out the matching for a UV theory that has a Caro multiplet and a Agostino. I don't know what happens for theories where you integrate out like two things at once. I don't know. Maybe there's nothing interesting in this, but at least, yeah, I've not tried to perform the most generic matching, so I cannot promise that I have the most generic form of the object of the Lagrangian you should add on top of the one that arises from the constraint. Yeah, this I wouldn't know how to do.
Another thing, one integrate out and does not find the same as the effective coupling. The effective coupling that one has used in, for instance, by CCWZ, WZ, or maybe some constraint. It's because the is not in the right region compatible with positivity bounds, or are nothing to do. Because I mean, in these old papers, those in the book of Weinberg of supersymmetry, there are old identities where the coupling seems to be with essentially with the energy momentum tensor.
Oh, right, good. Yeah,
with the energy momentum tensor. But you know, if you start from a Lagrangian with some terms which don't have mass, not always you get the same amplitudes that prescribed by decoupling with the T mu nu. It's because that probably the other constraints, the other possible coupling does not violate causality, or there is nothing to do with that. These were things that I was watching many years ago.
Yeah, sorry, let's see.
So, you know, this paper of David Friedman in 75, where the from the world identity and the soft behavior of Agostino, the main interaction was with the T mu nu of of the matter, but if instead one integrate out the super partners, the scalars, for instance, depending if there is mass or not, you don't get the same result at the level of amplitudes. This is because other possible couplings. I mean, could this be related with the positivity bounds or not? Or I'm not
I don't know. Sorry. Yeah, I understand what
more
you're
or less,
asking,
I'm
but
able to explain what I want to.
yeah, no, I understood. But I'm trying to remember in all the formula that we wrote if there's anything that can help. I don't remember. Sorry.
No, as you wrote at the start, the coupling of the Goldstino with matter involves the derivative of the fermion fields. So somehow the T mu nu is there.
Yeah.
And
that's right.
I mean, it is not always true that the only coupling at low energy is just by T mu nu.
Yeah.
It's because I think also in the paper of Bellazzini there is this. It's mentioned somehow this problem.
Yeah. It seems. Yeah, I think I've seen other kind of.
The other possible couplings are not respecting the positivity or what?
I think they're okay. Yeah. Sorry, I don't remember how they split into pieces, but I think in the case that respects positivity, there were couplings that didn't look like the T mu nu coupling, and they were perfectly fine. So I would say that other kind of couplings could be fine. Yeah.
Okay. Oh, well.
But yeah, I should need to. I would need to look it up again because it's been a while. Sorry.
It is not, however, something completely transparent. This aspect.
No, yeah, it was not. Yeah.
Okay.
I mean, it probably would if I looked at the formula a bit more again, but it's been. Yeah.
Okay. No.
Sorry,
Okay. If it is possible, we can continue discuss in another time.
Yeah.
I mean, maybe formulating better the questions. Okay. So thank you so much, Quentin.
Well, thanks. I'm sorry for the technical troubles.
Magnetic talk, and I mean, for us, it has been a great pleasure.
Sure. Well, for me too. Thanks.
Yes. So
Thanks.
we hope to see again in another opportunity.
Sure. Yeah.
See you. Ciao.
Bye. Thank you. Bye.
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 Bye.